Hey everybody, Mr. Cody here, and this video is on transformations of polynomials. So you'll remember transformations are ways we can change a graph. We talked about three main types of transformations. We talked about translations, which are shifts. So you can take a graph and you can shift it right or left or up or down. We talked about stretching a graph. Oops, my bad there. So you can stretch a graph to make it skinnier, or you can kind of shrink it to make it wider. And we also talked about reflecting graphs. So you can flip it over the x-axis or the y-axis. So you can do a reflection. Okay. And we've talked about these mainly in the context of a few different functions, but a lot of it had to do with parabolas, with quadratics. And we're just going to extend this idea to polynomials. Okay, so this shouldn't be too bad. Real quick review. Let's say you take f of x equals x squared, your normal parabola, and you write a new function, which is x squared plus 5. The question is asking us describe the transformation and then graph both of those. I hope we remember a plus 5 on the outside moves it up 5. Okay. Those outside transformations are vertical. It's outside the parentheses, and they work normal. Like a plus 5 goes up 5 and a minus 5 goes down 5. We were going to sketch these two. F of x is just y equals x squared. Well, that just looks like that. And then we can do it on a different graph, same graph, whatever. G of x, f of x, excuse me, is the same as f of x, but moved up 5. So it looked like that. Okay, and that would be 5. For this next one, x minus 1 squared, all in parentheses. That minus 1 on the inside is horizontal, and it works backwards. So that minus 1, you'll remember, moves it right 1. So f of x, oops, I'll do it. So f of x, again, would look like our normal parabola going through the origin, having the origin as its vertex. And x minus 1 squared would be a parabola that's moved right 1. So its vertex would be at 1, 0, and it'd look like that. And that'd be G. I hope you guys remember that. That was on your final. You guys did a good job with that. Here's a quick recap of things that you should know from previous chapters. Okay. If you do a minus on the inside, it moves it right. Plus on the inside, moves it left. Plus on the outside, moves it up. Minus on the outside, moves it down. A negative on the inside is a reflection over the y-axis, and a negative on the outside is a reflection over the x-axis. And then a number on the outside stretches it. If that number is less than 1, it shrinks it. Okay. Hopefully you remember that from previous chapters. Make sure you know how to do this in function notation as well, because I expect you to remember how to do it that way too. So looking at it like this or like that. All right. So how is this any different than what we've been doing? I'm going to add a couple of parent functions that you should know. Okay. Specifically, it would be good if you knew what x cubed looks like. So if you had a function f of x, equals x cubed, I'd want you to know what that looks like. And if you had a function f of x equals x to the 4th, I'd like you to know what that looks like. They're not too bad. I think some of you guys probably have an idea about these. X cubed looks just like this. I'll do it in different color. Okay. So it's kind of like half a parabola, but then instead of going up there, it goes down there. That's how I always think about it. And it goes right through the origin because 0 cubed is 0. X to the 4th looks like a parabola, kind of, but it's shallower at the bottom, and then it goes up steeper on the sides. So it's kind of like that. Okay. It'd be good to know what those two graphs look like because we're going to transform those around a lot. Okay. All right. So then a few problems here. Shouldn't be too bad. Describe the transformation of f of x equals x cubed represented by g of x equals x plus 5 cubed plus 2. And then graph it. All right. Well, plus 5 on the inside moves it left 5. Plus 2 on the outside moves it up 2. All right. Now I need to know that f of x equals x cubed looks like this. So that's what f of x would look like. So then g of x would look the same, except for it to be moved left 5 and up 2. And have that same shape. Nothing else would change. Just kind of that point that it wiggles through would change. Let's do one more like that. Oh, no, sorry, this one's a little bit different. So it says, hey, let the graph of g be a vertical stretch by a factor of 2, followed by a translation 3 of this function. And then write a rule for g. Okay? So we're trying to write this new function, g of x. It's going to be this guy transformed. How is it transformed? Well, it's stretched, and then it's shifted up 3. We need to make sure we do it in that order. So we're going to take our old function. And first, we're going to stretch it vertically by a factor of 2. We're going to multiply it by 2. Make sure we do parentheses. Next, we're going to move it up 3. How do you move something up 3? Well, you just add 3. There we go. Here's our new rule, our new function g. It's the same as f, except for it's stretched vertically by a factor of 2 and moved up 3. Okay. Let's run through a couple of other examples here. Let's say we started out with this polynomial f of x. Let's try and match these function rules with these pictures here. Okay, so if this was our original, then we would expect this to be the same graph moved right to. So looking around, looks like B would be the same as that right too. This one, the plus 2 on the inside would be left. Oops, sorry about that. Would be left 2. The plus 2 on the outside would be up 2. I take this and I move it left 2 and up 2. We can see. This one would be right 2 and also up 2. I think we're looking at D. So the last one must be A. Let's verify that. That minus 2 on the outside is just down 2, which is what A looks like. Cool. All right, I just want to do a couple more here. Same kind of idea here. Describe, actually, you guys can do these too. It says, describe the transformation and then graph each one. Once you pause, try those, unpause, and we'll check. Okay, so our transformations here were reflected over the x-axis and a vertical stretch by a factor of 2. The negative flips it over the x-axis. The 2 makes it twice as skinny. The blue would be our original. That would be what the x to the 4th looks like. And then the green is flipped upside down and stretched, make it a little bit skinnier. For this one here, the transformations are stretched vertically by a factor of 5 and then shifted up 1. This blue would be x cubed. And then the green there, you'll see is skinnier. And it's also moved, oops, it's also moved up 1. Okay. And that concludes this video.